All right, so what we're going to be talking about today are forward biased PN junctions. So let's say that I have a PN junction. And let's start with a junction at 0 bias. So I have bound positive charges on the N side of the junction. Bound negative charges on the P side of the junction. This distance is omega n, or excuse me, WN naught. This distance is WP naught. This is my neutral N region. This is my neutral P region. And in the middle here, I have my space charge layer or depletion region, where I have an electric field oriented from right to left, okay? So what I'm going to do is I'm going to apply a voltage drop across the sky. And I'm going to work all of the problems or whatever under this assumption here. Or this is our positive polarity terminal of our battery, and this is our negative polarity terminal. And then I'm going to say that we have some voltage here, V bias. And for these cases, our bias voltage is positive. Okay. So this is what we are going to be considering a forward biased PN junction. The high potential terminal will be connected to the P region, and the low potential terminal will be connected to the N region. All right. So, first question, we have a voltage drop applied across this PN junction. Where do we expect the voltage drop to actually occur? Across the depletion region. Can you back up that answer?
What we were talking about in last class, we were talking about how we'll have buildup right on the edge of the depletion, and the majority of barriers won't be able to pass through, so there has to be a drop.
Okay.
Over.
Okay, that seems reasonable. Another way to think about it, over here in the neutral N region, we have a very, very high concentration of electrons, right? If we have a very, very high concentration of electrons, what would we expect the conductivity to be? High, which means the resistance in this region, the neutral N region, would probably be pretty low, right? Over here on the P side, we have a whole hell of a lot of holes, which means we expect the conductivity to be high and the resistance to be low. So we should see a very small voltage drop over the neutral regions, and the remainder of the voltage drop will occur over the depletion region, right? Because we have some reasonable amount of resistance here because there are no free charge carriers or anything like that. Okay, so how does the polarity of this bias voltage relate to the polarity of the built-in voltage? What's the high potential side for the built-in voltage? Positive. The low potential side is the negative. So our built-in voltage is of the opposite polarity of our bias voltage, okay? So what that means is that when we apply a bias voltage in this configuration, we are lowering the barrier potential, okay? So our barrier potential overall is going to be V naught minus this quantity V bias, okay? Our barrier potential is reduced to V naught, our built-in voltage, minus our bias voltage. Okay. So if our barrier potential is smaller, what are some of the effects of that? Exactly right. Okay. So our built-in voltage V naught was all about maintaining equilibrium, right? It caused just enough drift to cancel out diffusion. Well, if we make that barrier potential smaller, we should observe that diffusion can more easily occur. Okay, so that's one thing, and we're going to talk about that in great detail in a couple of minutes. What else is going to happen? What were things that were related to that quantity V naught? The width of the depletion region depended on V naught, right? So if V naught gets smaller, the width of the depletion region also gets smaller. So effectively, these barriers or these edges of the depletion region move more towards the center of the crystal. Okay. So depletion region gets smaller. Where we can say that W, no longer W naught, because we are not at an equilibrium condition, W, will be the square root of, or actually I think I did it as to the 1/2 power the other day, so I'll maintain that. Twice epsilon over Q NA plus ND divided by NA times ND. And now we'll have V naught minus V bias, and all of this to the 1/2 power. Obviously, since the overall width of the depletion region has changed, the amount that the depletion region extends into the N side of the material and extends into the P side of the material also changes as well, right? The ratio isn't going to change at all, but the actual length into the crystal, right? So our relationship where Wn was a portion of W naught and Wp was a portion of W naught still hold, but the overall width of our depletion region has now gotten smaller. All right. So let's circle back around to what Logan was talking about, increase in the probability for diffusion by looking at the carrier concentrations. Okay. So if we have our crystal, like so. Where V bias is positive. What we should observe now is that the width of both of our portions of the depletion region are smaller. I'm going to call this direction X sub P. In this direction to the right, X sub N, representing the distance from the edge of the depletion region further into the crystal on either side, right? So for our holes on the P side, we should have a carrier concentration that looks something like this. Well, actually, that should be lower. Can't draw a straight line to save my life, so I apologize. And then for our electrons, should be something like that. So a couple of different things that I need to make note of here, all right? Over here on the left-hand edge of the crystal, we still have our unbiased thermal equilibrium hole concentration. And on the right-hand edge of our crystal, we have our thermal equilibrium hole concentration on the inside. Similarly, at the crystal boundaries for electrons, the same thing occurs. Here we'll have NP naught. Here we'll have NN naught. So I want to call this value in particular right here NP at a location X sub P is equal to 0. So this is the maximum value of the electron concentration on the P side. And similarly, this guy right here is going to be Pn at 0, which is the maximum value of the hole concentration on the N side. So what this region under the curve here, right? So this little roughly triangular region right here represents is excess minority carriers, right? So these are excess holes. And similarly, on the P side, we are going to have excess electrons. And so we should observe that we have some electron diffusion to the left and some hole diffusion to the right. This process is called minority carrier injection, okay? Because excess minority carriers have been injected into the N region. So excess minority holes have been injected into the N region. Excess minority electrons have been injected into the P region. And it's actually these excess carriers that wind up causing current to flow through our device, right? So notice the hole diffusion is to the right, which means we're going to have a diffusion current density oriented to the right. Electron movement and electron diffusion is to the left, which means we're going to have an electron diffusion current density also to the right. So they're going to add the total diffusion current densities are going to wind up adding together, and we should observe some total current flowing to the right through our crystal. Okay. So there's a little bump here in the carrier concentration for electrons at the edge of the depletion region on the N side. There's a little bump here in the hole concentration at the edge of the depletion region on the P side. So let's talk about where those guys come from, because they're providing a little bit of push, okay? The positive polarity terminal of our battery is going to do what to the holes on the P side of our crystal? It's going to push them deeper into the crystal, because the positive charge from the battery is going to repel the positive charges of the holes. So it's pushing carriers to the depletion region. Similarly, the negative polarity terminal on the battery is going to push electrons from the edge of the crystal towards the depletion region, enabling their diffusion as well, right? So we have things helping out such that diffusion will occur. And so that little uptick helps move the minority carriers across that small potential barrier. All right. So our minority carrier concentrations here, we should see, we have some initial amount of holes at the edge of the depletion region. And then as we move further and further into the N side, we should see that that carrier concentration decays, because those excess holes see all of the majority carrier electrons, right? So we are going to experience recombination, right? So we're going to have a lot of holes here. And then as we move further and further into the crystal, more and more recombination is going to occur. Same thing happens on the P side of the crystal. We've injected a bunch of electrons, so we see a very large amount at the edge of the depletion region. But as we move further into the crystal, the probability of recombination has increased. And so we should see that we have a decay in minority carrier concentrations as we move further and further in the X sub P direction. So mathematically, our carrier concentrations should look something like this, okay? So we should have P N naught, or PN, sorry, not PN naught, PN at X sub N is equal to 0 is PP naught, which is our whole concentration on the P side of the crystal, multiplied by the exponential of negative Q times V naught minus VF over KBT. So that's effectively just the barrier potential divided by the thermal voltage, okay? What does that exponential function bit there represent? You guys have had solid state electronics last quarter. Did you talk about Boltzmann statistics at all? Well, crap. Okay. That's very, very surprising to me. All right. So all this exponential function right here really represents is the probability that a hole will survive the space charge layer effectively. The probability that recombination does not occur in the space charge layer is given by this stuff. So we have some number of holes on the P side of the crystal multiplied by the probability that they make it to the N side of the crystal gives us the amount of holes at the edge of the space charge layer. Okay. And we can develop a similar relationship for electrons. NP at X sub N is equal to 0 will be N naught multiplied by that exact same exponential function. Negative Q V naught minus VF over ABT. All right. Now, what's pretty great about this is that we can simplify this guy to look like just the contribution of the, oh, sorry, this shouldn't be VF, this should be V bias. Sorry, I'm mixing things up. So we can make this guy look where we only see the effects of the bias voltage, okay? So this guy, our whole concentration on the N side is going to look like PN naught EXP of Q V bias divided by KBT. And over here, we're going to have NP naught EXP Q V bias by KBT. Okay. And these relationships come purely from manipulating the definition of our built-in voltage and how it relates the minority carrier concentration to the majority carrier concentration. We get to throw away the V naught bit and we get a positive exponential function that tells us how things behave here. Okay. So if we want to figure out what the current is, we need to be looking at our diffusion current densities, okay? And this is going to cause us to be looking at the diffusion length of our carriers, okay? So diffusion length, let me write this down here. L is the average distance traveled by a charge carrier before recombination occurs. So let me scroll back up here real quick. I didn't particularly draw this well because I'm incapable of doing it. But if we have a very long crystal like so, we should expect that the decay rate seen here as the holes recombine in the inside of the crystal and the decay rate here as the electrons are recombining in the inside of the crystal are effectively exponential functions, right? They're going to exponentially decay. And the rate at which they decay is directly proportional to the diffusion length for holes and the diffusion length for electrons. So let's see. We can define a change in minority carrier concentrations as a function of position to be the minority hole carrier concentration at some value of x sum n minus Pn naught or delta Pn at 0 exp of negative x sub n over L sub P. So this is telling us how the carriers decay from their maximum value down to the equilibrium minority carrier concentration for holes. And then we'll have effectively the exact same relationship for electrons. Again, all this is telling us is how far above that equilibrium minority carrier concentration we are. So we observe that we have some initial value that's well above our concentration, and then we have a negative exponential decay as we move further and further into the crystal because the number of minority carriers are decreasing, right? So we should be able to now determine the diffusion current densities. So for holes, we're going to have negative Q Vp times the derivative of the hole concentration on the N side of the crystal with respect to position on the N side of the crystal, which is the exact same thing as negative Q Vp times the difference that I've just defined. So we're effectively just throwing out, the constant portion. And so this is going to give us Q dP over LP delta P N at 0 the exponential of negative X sub N over L sub N. And we can do a very similar thing for electrons. Positive Q dN dNP of X sub N, X sub P is equal to Q dN d delta NP X sub P divided by dx sub P, or negative Q dN ln delta NP dxp negative X sub P L sub, and sorry, I made a mistake up here. Since these are holes, we should be using the diffusion length for holes, not the diffusion length for electrons. Okay. So I know this is a bunch of mathematical gobbledygook, so let me try to explain what's happening in words and make it make sense. Okay. Obviously, the diffusion current density for holes on the N side of the crystal depends on the hole concentration of the N side of the crystal. This is exactly the exact same, or this is exactly what we have here, except we're using this particular relationship because we don't care about the background level of holes we have on that side. We're only interested in the excess carriers. And that's exactly what this bit is here, right? Because it's only the excess carriers, the excess minority injected carriers that diffuse. And so when we substitute in all of our relationships from up here, this is effectively what we get. We have the charge of an electron multiplied by this ratio of the diffusivity divided by the diffusion length times the maximum number of excess carriers multiplied by a description of how that carrier concentration decays as we move further and further into the crystal. We have the exact same thing on this side, but we should notice here X sub P and X sub N are in opposite directions, which is why it looks like if we combine these two things, they're going to cancel each other, but that's not true, right? Since X sub N and X sub P are in opposite directions, these guys are going to add together and contribute to the overall current flow together. So they're not going to cancel at all. They add up to each other. One thing that is interesting here is that these current densities appear to be location dependent, right? So what do we know about the current flowing through a device? Should be constant throughout the entirety of the device. This seems to counteract that. But if we were to look at these representations mathematically, we would effectively wind up having something that looks like this. Okay. We're going to have to circle back around to a little bit more math in just a second, but this is our general positive X direction for the crystal. So way over here on the left-hand side is the P side. This is negative WP. This is positive WN. And we should see, let's see, for the electrons, which I've been doing in blue. All right, so for holes, we observe some amount of majority carrier hole diffusion current, right? Because holes are diffusing to the junction. If we assume that there is no recombination in this space charge layer, we'll have something like this. And then for electrons, it's going to be effectively the exact same thing. Where this guy right here represents the J diffusion N that we've just derived. And this guy right here represents the J diffusion P that we've just derived. And if we add these guys up, it's effectively a constant current flowing throughout the entire crystal. So this green guy is the total on top. Okay. So while the current density for holes and the current density for electrons does change as a function of position, the overall current density is maintained throughout our position in the crystal. Okay. So we know how things are behaving once they move across the space charge layer. Now let's tie everything together and talk about this portion of the majority carrier diffusion. All right. So J, D, H. All right. This is going to be our whole diffusion. Q, DH. Sorry, not H. QD. Dang it. P. Delta Pn at 0 is Q dP over LP Pn of 0 minus Pn naught which is Q dP over LP Pn naught exp q v bias over kBt minus Pn naught. And we can group like terms together and call this Q dP LP Pn naught exponential of, why is it not writing? Q V bias over kBt, close parentheses, minus 1. For our electrons, we can do the exact same thing, and I'm just going to jump to the end result. Negative Q dN over ln and P naught exp q v bias over kBt minus 1. And we add these guys together, we have Q dP over LP Pn naught plus Q dN over ln and P naught exp of Q V bias over kBt minus 1. And since we know the relationship between Pn naught and Np naught are minority carrier concentrations, this becomes Q times the intrinsic carrier concentration squared times dP over LP ND plus dN over ln NA times the exponential of QV bias over kBt minus 1. This equation, whole thing here, is known as the ideal diode equation. So it tells us how much current is carried with the total current, or really the total current density in a diode is. It depends on our bias voltage as well as the parameters of the semiconductor we use to make the diode out of. Right? This front bit right here JS is what's called the reverse saturation current density. Okay. And when we talk about reverse bias PN junctions on Friday, we'll see this guy again pretty darn quick. Okay. So effectively, we have some very, very small amount of current. This guy right here is usually on the order of 10 to the minus 12 to 10 to the minus 16 amperes. Very, very tiny, okay? Not zero, but very, very, very small. And then we have this exponential function. And notice that it is not a negatively decaying exponential, right? There's no negative sign out here. So for a bias voltage that is just a little bit larger than kBT over Q, our thermal voltage of roughly 26 millivolts at a temperature of 300 K, we'll see that the current being carried by this guy ramps up very significantly. We can very often ignore this -1 factor here at the end because this exponential grows so quickly that it doesn't particularly matter in the overwhelming majority of cases. Only when our bias voltage is a few multiples of the thermal voltage does that -1 bit even matter anything. For the overwhelming majority of the cases, absolutely doesn't. Okay. So jumping a little bit ahead, what we're going to observe when we get into diodes next week is a current voltage relationship that looks something like this. All right, so here is our current. I'm going to call this ID for diode current. Here is our bias voltage, and I'm only going to draw the portion where the bias voltage is positive because we haven't yet talked about reverse bias PN junctions. Gonna look something like this. There, large exponential growth. So for very, very small bias voltages, we get practically no current, but for very small bias voltages, less than our built-in voltage V0, we can see appreciable amounts of current. Let's talk about something theoretical here, okay? Before we move on to our last little topic for today, which is diffusion capacitance. So I'm going to scroll up a couple of pages. I'm not asking you guys to take any notes on this. I'm not going to test you on it or anything. I just want to talk about what's happening. All right. So here we have the equation for the width of the depletion region, which depends on V0 minus V bias. So what happens when V bias gets larger than V0? What if we were to bias our PN junction in such a way that we applied a voltage greater than our built-in voltage? Mathematically, that means we're taking the square root of a negative number. So do we get an imaginary width? No. We get a burnt out PN junction, right? Okay. So it's called punch through. All right. So effectively, we've made our depletion region so small that there is nothing to stop diffusion from occurring. So the current that goes through it is astronomically high. So like most diodes are designed for practical applications, are designed to carry a couple of milliamps of current. You get to this region of space because of the exponential growth, we're talking about multiple amps or more of current. It's just going to cause it to heat up so much that it's going to burn itself out. It'll never actually get there. So this is why you had to put a limiting resistor in your engineering 120 first day of class, making your diode or your LED blink. If you applied 5 volts to just the LED, that's well above the built-in voltage of it. turned on real bright for about half a second and then burnt out and you could never use it again. The exact same thing is going on here, okay? So in practice, the actual voltage drop over the PN junction by itself is going to be significantly less than the built-in voltage. But because the built-in voltage, which you guys, if you've done your homework and all that kind of jazz, know are somewhere on the order of half a volt-ish, maybe a little bit less, maybe a little bit more, depending on doping concentrations and all that kind of stuff. Half a volt is how much larger than thermal voltage. So let's call the thermal voltage 25 millivolts.
That's
20 times as much. What's e to the 20? Okay, calculator.
probably a million.
Let's see. 485,165,195. Okay.
That's
So-
theoretically the current that we're going to do.
Proportional to that, yeah. So not gonna burn it out pretty quick, okay?
Either that or the whole classroom. is gonna-
No, it's never gonna be like, there's not enough energy being dissipated for anything like that to happen. It'll just smell bad for a minute. But you'll burn out your diode pretty quick if you try to put a voltage anywhere close to the built-in voltage across it, at least as a forward bias voltage. Reverse bias voltage, large voltages are no big deal for the most part. All right, so the last thing that I want to talk about today, this class ends in 20 minutes, right? Okay. The last thing I want to talk about today is what's called diffusion capacitance, okay? So going back to literally what we were just talking about, if you apply a forward bias voltage to a PN junction, the width of the depletion region gets smaller, which means that the junction capacitance is going to do what? That's the capacitance that we talked about at the end of class on Monday. It will. The junction capacitance will increase for a forward bias voltage, okay? That's very rarely talked about. And the reason is the diffusion capacitance is a different type of capacitance that occurs only in forward bias junctions. And it's actually usually significantly larger than that junction capacitance can get, okay? So diffusion capacitance occurs because we have excess holes stored on the N side of the crystal and excess electrons stored on the P side of the crystal, right? So let me scroll up here. The area of this little triangle and the area of this little triangle represent stored charge. And the amount of charge that's stored is dependent on what that value of V bias is, okay? So we are going to have some diffusion capacitance because of that. And it's actually going to be reasonably large. So the total charge accumulated due to excess carriers is going to be QA times Ni squared times LP over, sorry, that shouldn't be a D, that should be an N. ND plus LN over NA times EXP of Q V bias divided by KBT minus 1. Okay, that's a total charge stored by those excess carriers. Our diffusion capacitance, C diffusion, is simply the derivative of Q total with respect to V bias. And so this becomes Q squared A NI squared over KBT. LP over ND plus LN over NA. EXP of Q V bias over KBT minus 1. So this is how our diffusion capacitance increases as a function of more and more forward bias voltage. So I have minus 1 written down. Let me think about it because I see what you're saying here. So when I take the derivative, all this crap out here is constant. When I take the derivative of the exponential function, that's where that extra Q comes from. Yeah, let's erase this. In the grand scheme of things, it's not going to matter if V bias is a little bit larger than the thermal voltage anyway. But yeah, I see what you're talking about, Jordan, so I'm going to erase it. Because the only term that has a V bias is this guy right here, and the derivative of that should just be Q times this exponential without the constant value. So you're probably right. I probably just made a dumb mistake.